This is Dr. J. Mohan. I am going to discuss about the signals and stochastic processing subject. In this subject, we should see the Fourier series of this session. Today presentation outline is Fourier series. Fourier series representation of periodic function of period capital letter T. Implementation. Important point on the summary. Trigonometric Fourier series, exponential Fourier series, relation between the trigonometric and the exponential Fourier series. Up to this much, today we should see this session. For the Fourier series, what is a Fourier series? The representation of Fourier series is called f of t. This is over the interval of 0 to t by linear combination of set of infinite number of mutually orthogonal function is called Fourier series representation. Fourier series is mainly divided in three types. First type is trigonometric Fourier series representation. Second type is exponential Fourier series representation. Third one is polar or cosine Fourier series representation. These are going to invented for the Fourier. Now we go for the Fourier series representation of periodic function of period capital letter T. For the first case, the trigonometric Fourier series we represent as a f of t is equal to a0 plus summation of n equal to 1 to infinity a of n cos n omega 0 t plus bn sin omega 0 t. Here a0, an and bn are Fourier series coefficient. This Fourier series coefficient we may represent for the a0 is equal to 1 by t integration of t0 to t0 plus capital letter T f of t dt. Then a of n is equal to 2 by t integration of t0 to t0 plus t f of t cos n omega 0 t dt. B of n is represented as 2 by t integration of t0 to t0 plus t f of t dt. That is sin n omega 0 t condition. Now we should see this is represented as a relation between the Fourier series. Now we go for the exponential Fourier series is represented as a f of t is equal to c0 plus n equal to 1 to infinity c of n e power j omega 0 t n plus n equal to 1 to infinity c of minus n e power minus j omega 0 n t. That c0 and cn and c of minus n are exponential Fourier series coefficients. The c0 is represented as a 1 by t integration of t0 to t0 plus t f of t dt. C of n is equal to 1 by t integration of t0 to t0 plus t f of t e power minus j omega 0 n t dt. C of minus n is represented as a 1 by t integration of t0 to t0 plus t f of t e power j omega 0 n t dt. This is the relation between the Fourier series of exponential as well as of trigonometric condition. Now you can see what the relation. So now we have for the Fourier series of trigonometric and exponential series. If we have for the any one the trigonometric or Fourier exponential series, we can convert it for the another type of Fourier series. Suppose if we find for the trigonometric, we find trigonometric Fourier series, we find based on that condition we find for the coefficients a0, an, bn. Then we converted for the trigonometric Fourier series into exponential Fourier series. We use this formula. Now a0 equal to c of 0. that is represented as a here exponential Fourier series what we are going to find in the C of 0. Then A of n is equal to C of n plus C of minus n, these two, C of n and C of n minus 2. So of exponential series, if we multiply both, we get for the A of n in the trigonometric Fourier series. Then if we need for the B of n, then that is equal to J of C of n minus of C of n minus 1. That means this both we may subtract, multiply with the J component. Then we get for the trigonometric condition. So at the same time, we have for the trigonometric series, trigonometric Fourier series, then we converted for the exponential Fourier series also, Fourier series coefficient. Then we say about C0 is equal to A of 0 for what you are going to finding for the A of 0 in the trigonometric, that both values are equal. Then if you need to find for the C of n of exponential Fourier series, we can take for the trigonometric Fourier series coefficient A of n minus J B of n divided by 2. Then C of minus n is equal to A of n plus J B of n divided by 2. This is a way we can convert it for the trigonometric Fourier series into exponential Fourier series or exponential Fourier series into trigonometric Fourier series. Then we go for the cosine Fourier series or polar Fourier series. The f of t is equal to d0 plus d of n summation of n equal to 1 to infinity cos n omega 0 t pi of n. Now this d of 0 is represented as a 1 by t integration of t0 to t0 plus t f of t dt. This d of 0 we may write like this one. Then we, based on this condition, we should convert it for the Fourier series of polar form into trigonometric Fourier series. Now d of 0 is equal to a0, d of n equal to root of a of n square plus b of n square. Then the d of n, if we get for the exponential series, then we need to find for the d of n is equal to 2 times of mod of c of n. This c of n, why we take for the mod of c of n in the sense, we get for the c of n comma c of n minus c of minus n from the exponential Fourier series. That's why we can write it here. So we know for that all the coefficient of trigonometric and exponential Fourier series. That's why we don't need to find for the polar series of d of n. We can convert it for the d of n into from your exponential Fourier series or trigonometric Fourier series. This is the Fourier series representation of periodic function of period capital letter T for both trigonometric and exponential and polar type. Next, we go for the important point of the Fourier series. So the signal, if we represent for the even, odd, hidden, rational, then what is the relation between the Fourier series of even condition and odd condition of Fourier series coefficients? First we take for the even symmetry condition. The even symmetry condition, even component A of n only is going to present. That's why A of n is exit. But odd component, whatever may be, have the odd component B of n equal to 0. Then you see here, if you have the even signal, only A of n only is present for the trigonometric Fourier series. Then remaining things, it will be consist as 0. So that will be represented as a even signal is represented as a of 1 only is present, then B of n is not present in the exponential series of trigonometric condition. We take the example of trigonometric. Next, odd symmetry. If odd signal is going to present in the signal, we need to find for the Fourier case, the A of n value is equal to 0, but B of n only is getting to exceed. The A of n equal to 0 in the sense A0 as well as of A of n, both is represented as a not exceed. Then only B of n is exist. Next, hidden symmetry. So its exhibit either even or odd symmetry is present. It may be present for the odd signal or it may be present for the even signal. Both is possibility, but either or one is going to present. Next, rational symmetric condition. If a of n at odd value of n in the even component condition, if odd component condition, v of n at odd value of n. These are the important point of symmetric condition in the Fourier transform. So here I take for the trigonometric Fourier series as an example. For all Fourier series, for exponential as well as polar or cosine transform, this is the general condition for even and odd symmetry of Fourier series condition. Now we go for the trigonometric Fourier series. In this trigonometric Fourier series, we should find for the periodic signals. So here I take for the periodic signal in the state, I should take for the two signal, that is represented as a sin n omega 0 t and sin m omega 0 t. Both the signals are orthogonal. The interval between that both the signal is represented as a t0 to t0 plus 2 pi by omega. This 2 pi by omega is represented as our capital letter T of n. Okay. So or here I write as a T0, T0 plus n capital letter of T. So the signal is going to start at for the T0. It's ended for the T0 nt. So this signal is continuously, this two signal, this is the signal limit, that is T0, T0 plus nt. These two signal, it's go for another case, in the sense another period, T0 to T0 plus nt period. This is for first period. I write here n equal to 1. Second period, I should write as a T0, T0 plus 2t. So each and every case, it will be going to increasing to that. So that's why what I am doing, general case, I take for the two signal. One is represented as a sin n omega 0 t. Another one is sin m omega 0 t. Both are orthogonal. Then the time interval limit is t0 plus 2 pi by omega n. This 2 pi by omega n equal to n t. Okay, we represent. This set is not complete without cos term, because this cos is set is also orthogonal to the sin set. So now what it will be represent? The signal, both the signal what we taken, that will be considered as a orthogonal together. If orthogonal, then the signal also possibility have for the cosine term. In this cosine term also is represented as a orthogonal set of sine term. So due to that case, what I am doing, both the signal, that is sine term as well as of cos term, I should take both, it will be represented as a orthogonal together. Then if orthogonal together, then what it will be going to happen? It's complete this set, we must include both cosine and sine term. For any function, except in the interval of this duration t0 to t0 plus 2 pi by omega 0 can be represented as the x of t, the signal what we taken for the orthogonal signal, this signal I should write as a0 cos 0 omega 0 t plus a1 cos 1 omega 0 t plus a2 cos 2 omega 0 to up to an cos n omega 0 t. Then another signal, that is plus, that is orthogonal together. Here I take for the coefficient as b0 sin omega 0 t0 b1 sin 1 omega 0 t plus bn sin n omega 0 t up to, it is represented as a b of n. That will be going to continue with up to, this is infinitive, this is also, it will be have the infinitive case. Now we write as a general condition. What is that? I write this general case, what will we do? Then based on the 0, 1, 2, 3 of cos term, sin term of 0, 1 to 3, I am going to simplify. If cos 0 is represented as a 1, then A0 only is present. A0 into 1, I write is A0 plus E1 cos 1 omega 0 t plus E2 cos 2 omega 0 t plus an cos n omega 0 to up to it's going to have the infinitive. The b term also, the sin 0 is equal to 0, then b0 is getting to cancel, then plus of b1 sin 1 omega 0 t plus up to bn sin n omega 0 to, this is also we have the infinitive. Now I write for the simple cases. So here a0 is there, you take it out for the a0. For the remaining, this is also complete, this is also n signal is infinity, this is also n signal infinity. I should write as a n equal to 1 to infinity, a of n cos n omega 0 t plus b of n sin n omega 0 t. Now, this interval, the signal interval, where it will be going to happen, that is t0 less than t0 plus capital letter T. So, this is one period. If you need for the another period, that is t0, then t0 plus 1t. If you need for the another period, here you change for the 2. So, like that one, it will be going to continue together. So, now what will be here present? We taken for the two different signal, that is sin and n of sin omega t and sin m of omega 0 t. Both are orthogonal. The interval between the signal is represented as t0 to t0 plus 2 pi by omega n. Then, if you take for the sin term, it's not going to complete it without cos term. That's why I represent this. It's not complete without cos term. So now, if we going to have the cos term in the sense that sin term and the cos term both it will be going to orthogonal together. If both the orthogonal, I should write the signal as x of t. That x of t is equal to a0 summation of n equal to 1 to infinity a n cos n omega 0 t plus b n sin n omega 0 t. That limit is present for the t0 less than t0 plus 1. If we go for the another signal, here you substitute for the n. The n is represented as 1, 2, 3. That is t0, t0 plus 1 t. t0, t0 plus 2t. So many harmonic is going to possible together. So this is represented as a trigonometric Fourier series. This form is represented as a trigonometric Fourier series. This trigonometric Fourier series have for the coefficients a0, an, bn. So we need to find it. If we go find for the trigonometric Fourier series coefficient, you must know what is the orthogonal. We studied for the orthogonal in the first model. What is the orthogonal? We received the two signal, that is that will be represented for the C1, that is represented as a, we consider as a vector, that is V1 and V2. So two vectors are there, both it will be going to joining together. Then this value, this thick line I call for the vector space, this dotted line I call for the magnitude value. So both the vector is going to acting for the different direction, even though both the vector going to have for the magnitude as well as a direction. So the direction we represent by the thick line, the magnitude represents as this dotted line. So now this dotted line C12 I consider as the magnitude of 1 and 2 vector C12, it's multiplied with V1. So this magnitude value of the vector position I represent as C12 dot of V1. So now we need to find for the C1. If C12 represent as a orthogonal vector between the V1 and V2. Now I write for the C12 is equal to integration of T1 to T2 F1 of t, F2 of t dt. This F1 of t I consider as a cos term or sin term. The F2 of t consider as a sin term or cos term. Okay, you can consider for anyone. Because of we are taking for the two signal, the two signal it's represented as a orthogonal together. Whether if you have the sign in the sense, sure it will be have for the cos term also. If you have the cos term in the sense, it's going to have the sure in the sin term. So both the signal it's represented as orthogonal together. Based on that condition, we need to find for the magnitude of C12 of the two vector. The C12 is equal to integration of T1 T2 F1 of t into F2 of t dt divided by integration of t1 to t2 f2 of square of t dt. This is second signal. That second signal we consider as a v2. Okay, this is the condition we take. We need to find for the coefficient value of trigonometric Fourier series. The trigonometric Fourier series of two signals is orthogonal together. Then only is possible to find for the Fourier series coefficient. That coefficient is represented as a magnitude value. So here A0 as a Fourier series coefficient, An is a Fourier series coefficient, Bn is represented as a Fourier series coefficient. A0 is represented as the coefficient is equal to orthogonal together. That's why the interval, what we studied for the interval for the previous case, we studied for the t0 to t0 plus capital letter T. So here we use for the n, how many signal, how many period we need, then you can utilize for this n, 1, 2, 3, 4, 5, 6, like that one. So now the Fourier series coefficient as orthogonal function, the interval between t0 to t0 plus t of integration x of t, we take for the x of t, then another signal is represented as a cos or sin term based on this condition. Now the f1 of t I consider as a input, f2 of t is represented as cos or sin term. There is no angle is present. That's why I write for the one tt. Then after we take for the f2, that f2 is present for the f1 and f2, both it will be going to happen for the same line. There is no angle is going to happen between the v1 and v2. So that's why I write for the which signal is present, f2 or f1. So I write for the 1 square dt. Then integration of 1 square dt, integration of t0 to t0 plus t1 dt, this value is represented as a 1 by t. So this integration is represented as a t. After integration, after substitute for the t0 plus t, we get t. So this t, I take it out, 1 by t. The remaining portion, what is that? So integration of t0 to t0 plus t x of t dt is there. This is a0 of Fourier series coefficient. This a0 Fourier series coefficient is represented as a magnitude value of two signal orthogonal condition of initial state, that is a0. Next we go for the next state. This an, what is that? An is present for the n equal to 0 to infinity, n equal to 1 to infinity. So due to that case, we may find for the magnitude coefficient, that is a of n is equal to integration of 0 to t0 plus t x of t. Same we are taking. This is a of n. What is it? This is represented as a even values, that it will be considered as a cos n omega 0 t dt. So the even value only we need to take for the integration of bottom side. Integration of 0 to t0 plus t cos square n omega 0 t dt. So this portion have for the trigonometric integration equation, that value is represented as a t by 2. If this instead of cos square, we take for the sin square, that also is represented as a t by 2. So you take, if we do for the integration for both, that is integration of t0 to t0 plus t cos square n omega 0 t dt is equal to integration of t0 to t0 plus t sin square n omega 0 t dt, that value is equal to t by 2. Here you can substitute, you are getting for the output as a b of n is equal to 2 by t integration of t0 to t0 plus t x of n cos n omega 0 t dt. This is a of n. B of n is equal to 2 by t integration of t0 to t0 plus t x of t sin n omega 0 t dt. So we got for the coefficient of Fourier signal b of n, e of n as well as of p of 0, as this case is considered with the orthogonal condition. Next, we go for the exponential Fourier series. A set of complex exponential Fourier series is represented as a e power j n omega 0 t. Now n is present for the 0, plus or minus 1 and plus or minus 2, up to it will be have the infinitive. So here also we consider as a orthogonal over the interval. The orthogonal condition, the interval is represented as a t0 to t0 plus capital letter T. Now capital letter T I should write as a 2 pi by omega 0. This is a complex set, so it possible to represent for the any function f of t. I write as a f of t is equal to f of 0 plus f1 of e power j omega 0 2 plus f2 of e power j omega 0 t into 2 time plus up to f of n e power j n omega 0 t. It's going to happen for the up to infinity. And what we done for the case of your positive side, same to be happen for the negative side also because of orthogonal together. So f of minus 1 e power minus j omega 0 t plus f of minus 2 e power minus 2 j omega 0 t up to f of n minus n e power minus j n omega 0 t up to it's going to have infinity. We need to simplify for this equation. I should write for the general case f of t is equal to n equal to minus n to plus n f of n e power j n omega 0 t. Now the t, that is a time interval between the two signal, is represented as a t0 to t0 plus t. This is a exponential Fourier series representation of signal of f of t over the time interval of t0 to t0 plus t. So f of n is represented as a exponential Fourier series coefficient. Next case, we need to find for the exponential Fourier series coefficient. The signal we consider as a orthogonal function or orthogonal signal. So it's have the two different kind of signal. One is represented as a f of n and another one is represented as a f of minus n. These two are getting to orthogonal together. Then if we need to find for the f of n, it's represented as a orthogonal set condition of magnitude value in the exponential Fourier series. We should write for the orthogonal condition as integration of t0 to t0 plus t as our time interval of the signal, that is t0 to t0 plus t. Here it will be represented as a n. How many number of period we are going to using, that n we are going to take here. Generally we write as a t0 to t0 plus t. So due to that case, we take for the integration of t0 to t0 plus t f of t e power j n omega 0 t star dt divided by integration of t0 to t0 plus t e power j n omega 0 t into e power j n omega 0 t star. Here we take for the star value of both. Why in the sense? Because we represent as a orthogonal together as f of n as well as f of minus n. So instead of minus n, I should use for the star value. Then we can simplify for this equation. So this two, what will be happen? These two getting to cancel. This two, because of here we get for the minus. If we remove for this one, we get for the minus. These two are getting to cancel. So then finally what we get? The integration of the uppercase integration of t0 to t0 plus t f of t e power minus j n omega 0 t dt. This two part is getting to cancel. E power 0 is represented as 1. I write like this one. Integration of t0 to t0 plus t f of t e power minus j n omega 0 t dt divided by integration of t0 to t0 plus t 1 dt. If we integrate this case we get for the capital letter T. So this I should write as a 1 by t integration of t0 to t0 plus t f of t e power minus j n omega 0 t. This is we called as a exponential Fourier series coefficient. So what depends upon the case. If you are going to apply a minus here, then you should apply for the minus of n here instead of plus n. Then we get for both the coefficient f of n as well as of f of minus n. So this condition also we consider as a orthogonal together. Next case, the relation between the trigonometric and exponential Fourier series. So now the signal x of t we consider as a periodic signal. The Fourier series is going to suitable only do for the periodic signal. If the signal is periodic, then the period I should take for the t0 to t0 plus nt. So this n is represented as a depends upon the which period we are going to take. Okay. So based on this condition, I take for the trigonometric Fourier series and exponential Fourier series representation as x of t is equal to, I write for the exponential Fourier series that x of t is equal to a0 plus summation of n equal to 1 to infinity a n cos n omega 0 t plus b n sin n omega 0 t. Now the exponential Fourier series I should write as a x of t is equal to summation of n equal to minus infinity plus infinity f of n e power j n omega 0 t. Now I should expand for the exponential Fourier series. So that is f0 f1 e power j omega 0 t plus f2 e power j 2 omega 0 t plus dot dot plus f of n e power j n omega 0 t up to it's going to have the infinitive. Then the minus side f of minus 1 e power minus j omega 0 t plus f of minus 2 e power minus j 2 omega 0 t plus dot dot plus f of minus n e power minus j n omega 0 t up to it's going to have the infinitive. Okay. Now I need to simplify for this case. So e power j omega 0 t is represented as a, that is e power j theta is equal to sin theta. Sorry, this is e power j theta is represented as a cos theta plus j sin theta. I should write like this format for this portion. For every portion, I should write like to for the Euler form. So this is first f0 plus f1 cos omega 0 t plus j sin omega 0 t for this case. For this case, plus f2 cos 2 omega 0 t plus j sin 2 omega 0 t up to I should write for the n as a infinity stage up to is going to have the infinitive. Then the minus side also I should use for the same notation, but here is minus, that's why you write for the minus here. Okay. So f minus 1 cos omega 0 t minus of j sin omega 0 t. Then second portion, this is f of minus 2 cos 2 omega 0 t minus j sin 2 omega 0 t up to you should write for the infinitive. Now we got for the complete set of the equation. Now we compare with the trigonometric Fourier series into exponential Fourier series condition. So I should write for f0 plus f1 plus f of minus 1. The cos term for here is same for here. For f here the cos term, these two cos term are similar. I take it out for the coefficient f of n plus f of minus n. I take it out for the f of cos 0 omega t. Okay. So here f0 plus f1 plus f2 coefficient I take it out. Then the common term is cos 0 cos omega 0 t. Same like that one. I write for the all the terms up to is represented as infinitive. In the second case, the j term we need to write. See the here the j term is going to pending. So here also we have the j term is going to pending. What is it? The f of n, that is represented as f of minus 1 as well as of f of 1. Both it will be going to have for the sign time also. Then what we write? F of 1, this minus sign I should write for here. That is f of 1. The j I take it out, f of 1 minus of f of minus 1 sin omega 0 t. So like that one I write for the all the term. Then now I compare with the our Fourier series condition of trigonometry. That we need to compare. That's why x of t is equal to f0 plus summation of n equal to minus plus 1 to infinity f of n plus f of minus n cos n omega 0 t plus j f of n minus f of minus n sin n omega 0 t. Now this term, see this is represented as a exponential Fourier series. This term, what is it? This term it will be going to compare with trigonometric conditions. For here, what is it? A of n. Then this f0 is represented as a of 0. Then this b of n is represented as a f of n minus f of minus n. So I should write here a0 equal to f of 0, an equal to f of n plus f of minus n, bn equal to j f of n minus of f of minus n. I should write. Okay. See the table for we write for the previous case. In this case, see, I should be taken for the trigonometric Fourier series. Okay. So the trigonometric Fourier series a0 equal to c0. There we used for the f. At the same time, an equal to cn plus c of minus n. So this is a0 equal to f0. I am using for the f0 in the derivation. A of n equal to f of n plus f of minus n. The b of n is equal to j f of n minus of f of minus n. This value we got it from the as per the derivation for this condition. See, so a0 equal to f of 0, an equal to f of n plus f of minus n, bn is equal to j f of n minus f of minus n, and finally I write as a f of n. Okay, I need for this f of n. So what do we represent? F of n equal to 1 by 2 an minus j bn. F of minus n equal to 1 by 2 an plus j bn. This one also we studied for the table. For the relation between the Fourier series of three different. See here, C0 f of 0 is equal to a of 0. I write. Then C of n equal to an minus j bn divided by 2. C of minus n equal to an plus j bn divided by 2. I wrote here. So same it will be going to exist for here for our relation. So 1 by 2 f of n is equal to 1 by 2 an minus of j bn, f of minus n equal to 1 by 2 an plus j bn. All it be going to exist. So this is a way we can convert for the Fourier transform as exponential to trigonometric or trigonometric to exponential, or this is a relation between the Fourier transform of trigonometric and exponential Fourier series condition. Next, take for the some example. Find the trigonometric Fourier series for the periodic signal x of t as shown in figure. Here I take for the square wave. The square wave consists of amplitude is equal to 1. The interval between the one complete period it's represented as minus 1 to plus 3, or you should take for the 1 to 5. So anything you may take, because of the Fourier series is possible to do for the only periodic signal. So first we can find this signal is periodic or not. So the signal is periodic only. Why? Because of same it will be going to repeat it for the different way. Here I write for the different way together. So what the period is present minus 1 to 3, same is going to happen for the 3 to 7. Okay. So same will be happen for the 7 to 10. So the signal values are similar. So that's why this is represented as a periodic signal. Now, if the periodic signal, we need to find for the time period. What the time period? We take for the one complete signal. Okay, minus 1 to 3. Then interval between the 1 and t, 1 and plus 3 is represented as a capital letter T. Okay, that is represented as a fundamental period of the signal. Okay, we need to do the solution. See, first we find for the capital letter T. This T we need to find. Where it will be going to happen? Minus 1 to 3. Okay, so actually what the fundamental period we need to identify, what the end signal minus of what is the start signal we need to write. I write for the here is 3 minus of what the here is represented as a minus 1. The starting period is represented as a minus 1. I should write for the minus of minus 1. So the total period of our signal is represented as a capital letter is T is equal to 4. So that is one period. So one period is represented as a 4 division it will be going to happen. Next, we should go for the omega 0. So the omega 0 is equal to 2 pi by t. We studied for the signal condition. So omega 0, we studied for like this one, omega 0 equal to 2 pi by of t we studied. So 2 pi by t, that is pi by 2. Now the omega 0, analog signal omega 0 equal to pi by 2. Okay. After that, we need to evaluate for the signal. So A0, we know the formula of trigonometric Fourier series, that A0 is equal to 1 by t integration of T0 to T0 plus capital letter T x of t dt. Now we need to take for the period. What is the period? 1 by 4. It's happened for the minus 1 to plus 1 x of t. X of t value is equal to amplitude is equal to 1. I write for the 1 for this case. So up to minus 1 to plus 1, it's represented as a plus 1 here. Okay. So otherwise, I will explain. I take for the one period of the signal. So what the one period? It started for the minus 1. The amplitude is equal to plus 1 up to 1. Minus 1 to plus 1 is amplitude is equal to 1. Then plus 1 to 3, the amplitude equal to minus of 1. Now, based on this condition, I should write for the equation for here. 1 by 4, that is t is equal to, we find for the 1 by 4. Then integration of this interval, I take for minus 1 to plus 1. Based on the signal, I take it out for the one period of signal. Minus 1 to 1, the amplitude is equal to 1 dt. The x of t value is equal to 1 plus the integration of 1 to 3. The x of t is equal to minus 1. 1 to 3 minus 1 dt. Now we do for the integration. If we do for this integration, that is 1 by 4, is take it out the common t. Substitute the interval of minus 1 to plus 1 minus of this minus, I take it out, minus of 1 t. The interval of 1 to 3 we need to substitute. After substituting all the value, this is represented as a, that is A0 is represented as a 0. Why? Because of this is 1 to minus of minus 1. This is represented as a 2 minus of 3 to 1. This is 2. This is 2. This is also 2. 2 minus of 2 is equal to 0. 1 by 4, 0. A0 now is represented as a 0. Next, evaluate for the A of n. The A of n formula you know, 2 by t integration of t0 to t0 plus t, then x of t cos n omega 0 t dt. This omega 0 we find. Okay. In the derivation we use for the omega 0. But here I am using for the omega 0 t, because we know whether this analog condition I took for the omega 0 t. Then the same position of interval of our signal, minus 1 to plus 1, plus 1 to 3. I write for the 2 by t is represented as 4, integration of minus 1 to plus 1 cos n omega 0 to dt plus 1 to 3 integration minus 1 cos n omega 0 to dt. So this is plus 1, this is represented as a minus 1. Then go to the next step. 1 by 2 sin n omega 0 t. You should differentiate with the case n omega 0 t 1 to minus 1 minus of sin n omega 0 t 3 to 1 n omega 0 t. Then we should substitute for the both upper as well as up lower limit. Then finally we got for the output is like this one. So 1 by 2, 2 divided by n pi sin of pi by 2 n minus of sin n pi by 2 minus 1 minus of sin n pi by 2 3 minus of sin n pi by 2. So you can simplify for that all the limit substitution. Then we got for the A of n is equal to 4 by n pi sin n pi by 2. Then should evaluate the B of n in the same condition we took. The formula B of n equal to 2 by t, t0 to t0 plus t, x of t sin n omega 0 t t dt. Then substitute for the both the limit, what the limit, the condition minus 1 to plus 1 as well as of 1 to 3. Then make to integrate and substitute the interval. Finally we got for the B of n equal to 0. Then finally I should write as our equation as trigonometric Fourier series condition. X of t is equal to a0 plus n equal to minus n equal to 1 to infinity an cos n omega 0 t plus n equal to 1 to infinity bn sin n omega 0 t. So this b0 is represented as a 0, then a0 also is represented as 0. Only these terms are there. A of n you can substitute. At the same time omega 0 we know, that is pi by 2 you can substitute here, cos n omega 0 t. So finally we get for the x of t equal to this equation. So omega 0 we know for the condition of based on the t is equal to 2 pi by omega. So that is n equal to minus 1 to plus 1, that is x of t is equal to n equal to 1 to infinity 4 by n pi sin n pi by 2 cos n pi by 2 t. Up to this much I have concluded for this session. This session we studied for the Fourier series. This session we studied for the Fourier series, type of Fourier series. The Fourier series consists of trigonometric Fourier series, exponential Fourier series, and a cosine Fourier series. At the same time, what are the relation between the exponential as well as of cosine Fourier series we studied. Then we studied further some important point of symmetry condition. Then we find for the relation between the trigonometric and exponential Fourier series and work out for the one example. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.